New wires around my glasses. I feel checked in. Okay? Okay. So hi everybody. Today I'm going to talk about a project that I'm really happy about. I'm really happy that it exists. And it's not my work. Bas and his brother did it at LumiGuide, which is his company which is doing really cool stuff regarding bicycle parkings. And I watched this talk by him a few months ago, and I was really happy about it for various reasons. The main reason is that OpenCV is this computer vision library. I will mention briefly what I can do, but it's like really useful. In that field, when you need to prototype something, you probably reach for it. Yeah, the other thing is that it happens often, and this is another data point in this pattern, that when you write a Haskell library wrapping on some functionality that is sort of written in some other language or some database or some sort of resource, the Haskell version often ends up being better in terms of API than the original version. And I think this is an example of this scenario because we're able to be more expressive in our types, so we're able to describe better what the functions do at the type level. The other reason I was happy to talk about this is because a year ago I gave a talk at Haskell Exchange about this library called inline C to write C code from Haskell, and Bas, it was a big enabler in writing this library, so there's a sort of continuity here. It's like an open source success story or something like this. So yeah, I think it's a nice example of things working out well in that regard. So yeah, the first slide 1 year ago was that in many scenarios, in many fields, it's not really the language that enables you to work, but it's some sort of toolkit that it's considered like indispensable to get stuff done. So in computer vision, in image processing, there is like OpenCV is a big thing in the sense that like there is a lot of stuff that makes your life easier. In statistics, you might have R or maybe the Python libraries. In numerical computing, there are many numerical libraries, but you really want this sort of power at your disposal without having to implement almost anything. You just glue pieces together and you get stuff done. But in Haskell, we don't have many of this. So yeah, we were trying to make prototyping programs in Haskell using these libraries easier by creating easier ways to bind to foreign languages. So inline C is part of that thing. Matthew is presenting actually in the same track, inline Java, I think it's called. I haven't actually worked with him on this, but there's this, like, we're trying to make it easier to use this sort of resources from Haskell, because Haskell is lacking this library just because these libraries take a huge amount of time to write. And so one of these libraries is inline C, and it's like this kitchen sink library for computer vision. And yeah, it's just this huge collection of algorithms that were implemented for you to do image processing, computer vision, all sorts of stuff. So for example, it's got like image filters like blurring or like flood fill or like edge detection, this sort of stuff. It's got more advanced stuff like feature detection for stereo matching or even face detection, face classifiers, this sort of stuff. It also has a lot of like very practical utilities that should not be underestimated. For example, to decode images, right? Or to get a feed from a webcam or this sort of stuff. OpenCV makes it very easy. So it's really a big enabler of applications in this space. And I've used it many times to do this sort of stuff. And it's usually from Python and C++, probably Python if you want to get started quickly. So OpenCV really sort of gravitates around one main type, which is called mat, which is the type of matrices that OpenCV defines. And this mat type, it's really the main vehicle of data in OpenCV. So images are two-dimensional matrices, but also with each element being a pixel, obviously. But also, if you have transformation matrices, you use the same type. It's generally like the thing that you find the data in OpenCV. And the first thing I want to talk about, and this talk is going to be in two parts. First, I sort of give an overview of what these bindings look like, and then I give a live demo to show you how easy it is to get like interesting results out of it. And really, the main work also in the Haskell bindings was to find a Haskell equivalent at the type level to this mat type. And in OpenCV, the mat type is very opaque. It's just you have a matrix, right? But it's very dynamically type in terms of what the math looks like. I think, actually, I haven't used the C++ API recently, but I'm pretty sure it's that way. In Haskell, on the other end, we can describe very clearly the shape of this matrix. And this is the first thing I want to talk about because I think it's just very convenient. And this is a pattern that I see more and more because we're also, like in my work, I'm also doing a lot of numerical computing, and generally, like with these matrices, the situation, apart from in C++, actually, where there are libraries that let you be really strongly typed about the shape of the matrix, it's usually very messy, and it gets hard to keep track of the space they live in, or like the dimensions, the dimensionality of these matrices. So in Haskell, we can do better, right? I've written the definition, well, the type definition of this matrix type. So each matrix has got 3 type parameters: the shape, the channels, and the depth. The shape is the dimensionality of the matrix, and like, for example, you might have a 3x3 matrix, and then it will be a list with 3 and 3 in it, or it might be, higher, like it might be 4x4x4, and then you got 4x4, or it might be one dimension, right? So you might have just simply one number in this list. But yeah, shape is basically a list of numbers telling you how big each dimension, how many dimensions and how big each dimension is. The channels is how many, this is sort of image specific. The channels is how many values each pixel contains. With RGB is going to be 3, with, RGBA is going to be 4, with grayscale is going to be 1, and also for normal matrices used for mathematical purposes, it's going to be 1 as well. Finally, the depth is the values that the pixels contain. So again, for RGB on these sort of image types, it's going to be word 8 from 0 to 255. But for more general purpose matrices, it might be double or it might be int. Like there is a lot of, it can contain a lot of things. OpenCV dictates what it can contain, but it's like definitely words of various sizes, integer of various sizes, floating point numbers, like single and double position, and so on. So let's refine that type definition slightly. So I'm not sure exactly like how much you're familiar with this sort of notation, but basically in recent Haskell, you can give you can give let's say a type to each type parameter. So basically what we're saying here is that usually all type parameters in Haskell have the kind type, right? So for example, if you've got maybe A, the A there is a placeholder for a type like bool or int or whatever. But in recent Haskells, you can go beyond that, and you can actually say, okay, these type parameters, both in functions and in data types, actually represent some value at the type level. So considering what we've said, the shape is a list of natural numbers, right? So, could be a list of 1 or list of 1 and 3 or whatever. The channels is just a natural number, so maybe 1 channel, 3 channels, 4 channels, or whatever you want. And the depth is an actual type, right? Like word date or double or whatever. Now then, there is a bit of a problem though, because this definition assumes that we know everything that we want to know about the matrix at compile time, right? You cannot express with this scheme, for example, an image of unknown size. It's got to be something that you know, because the type of shape is a list of natural numbers. So how do we solve this problem? And by the way, if there are any questions, I can imagine that this sort of notation for some people will be confusing. So if you have any questions or you want clarification, please just interrupt me.
I have a question.
Yes?
Having channels be a map seems to be not enough information.
You want it to be positive?
No, it could be RGB or CMY.
Yes, good question. So right now, we don't encode, the type parameters are limited to very sort of data layout sort of matters. What you're talking about is that the question was, by the way, shouldn't we actually encode in this type variable what color space it lives in? This is sort of additional information. It's like, I know this matrix is RGB. An RGB matrix is exactly the same layout as a BGR matrix, but I know that it's not the same. And right now, the library does not let you do that. I think it was just a matter of writing the first version in the most straightforward way. I will show later that the library has facilities, has actually a mapping from color spaces to channels, but not the other way around in this case. But that's a good question. We could. In fact, even with matrix types, they usually encode only dimensions, but it's often very convenient to encode what space they represent, right? So for example, if you have a lot of camera poses, and you have matrices, transformation matrices represent the camera poses, we found very useful in our work to tag them with a phantom type representing with a camera ID that tells you not only that it's a 4x4 matrix, but it's also that camera. So thank you, good question. Any other questions regarding this type? Yes?
Is there a reason why the shape is a list and not just a tuple of a pair of values?
We might have 3 or more dimensions. Or 1.
Okay.
All right? Okay. So the question I was asking was, what do we do if we don't know all of this information at compile time? And what we do is that we have a maybe type. It's exactly the same as the maybe type, but like it's not the maybe type for clarity and also for brevity, because it's just one letter. That tells you if something is dynamically known or statically known. And then we just apply it to all the type parameters here. So we say, we might know or might not know how many dimensions there are. And for each dimension, we might or might not know how big it is, right? Same for the channels, same for the type. So you might have some metrics that you don't know the type of the values are, right? So this lets us, for example, when you decode an image or something like this, that you don't know anything about the metrics. You might know that it's two-dimensional, maybe. You don't know if it's grayscale or RGB. You don't know. You just don't know a lot of things about it. So it lets you treat this data, which is not statically known yet, in a comfortable way. These are just some examples. The first type is the one we use most when dealing with images. It's a two-dimensional matrix. The size of each edge is unknown. We just want to manipulate all such images. It's got 3 channels, and the depth is word date. So 0 to 255. So that's like when you're dealing with images, at least I find myself dealing mostly with that, and maybe S4 if you've got an alpha transparency channel. The second one is just an example I made up. It's a 420 by 680 image with 4 channels. So this might be an RGBA screenshot if you had a really old monitor. Finally, well, not finally, this is a transformation matrix for 2 by 2 vectors. But depending on how you work, it might be 3 by 3 or 2 by 3. And it's got 1 channel and doubles inside. And this last example is an array of floats of unknown size. Is there?
I need to interrupt you.
Sure.
You can carry on speaking if you want.
Yeah, no, it's okay, because I need to switch slide.
So it's just we need to record your presentation.
Ah, okay.
We cannot see your slide in there.
I see.
It's going to take 30 seconds.
Yeah, that's fine. Any other questions in the meantime? Maybe. Yes?
So the other way of dealing with this kind of situation where you don't... the other way of dealing with this situation where you don't statically know this kind of information is to use basically existential types.
Thank you. Yeah.
As opposed to sort of encoding in the type itself the possibility that some information may be
Yeah,
available.
right.
Can you compare the two in terms of...
Can I compare the two? So, okay, with an existential type, the first thing that comes to mind is that you definitely need a type class or a constraint that lets you sort of, well, do you? So what do we want to do with these dynamic things? The things you usually do, I mean, you're super familiar with this, is that when you deal with dependent types, you want to start with something unknown and then gradually refine it to something which is more known. If you just had any type there, I guess you would probably be fine. I mean, one advantage is that dealing with monomorphic things is generally easier. So let's say you've got a list of these, right? You could not have a naked for all in a list, right? At least not in Haskell. Let's say that you wanted to handle lists or data structures containing dynamically sized things. In Haskell existential types, it would be a bit annoying to place these existentially parametric things in well, the list example is a common one, right?
Can you unify these two? So,
Actually, let us finish first the existential thing. I don't know if is this related? So, okay, so what is the question?
so can you unify, let's say,
Unifying the unification sense, like
the statically known and the dynamically known value?
no, you cannot treat one for you cannot use one for the other. What happens often, though, is that you have functions accepting any dimensions, as we will see. So that's how you usually do it. Then I think your question will become clear soon. Like the answer to your question will become clear. What you're saying is that with existential types, you will be able to use those unknown things in place of anything.
I think so. It's fine.
I think that's what you're asking, right? Right. No, you cannot do this here. It's in practice, it's not a problem because the functions that manipulate these values range over any dimension, right? So you don't often want that. I think as I show a bit of type signatures, it will become clear, like what this looks like. Sorry, I just need to slideshow this. Okay, so let's show an example of a function handling these things. And this function has a lot of features, so that I can actually show what this programming looks like. Okay, so this is Gaussian blur. It takes an image. And these types are slightly simplified, removing the constant parameters, but they're the same as what you find in the library. So I've removed the parameters of the algorithm just for clarity. So okay, what does a Gaussian blur do? It takes the size of the blurring, right? For each pixel, it's got a range in which to do the averaging, basically, which is this vector. This V2 is like a tuple with two elements. It's like the same thing. Then it takes a matrix and it outputs a new matrix. But there's a lot of things going on here, so let's just analyze them. The first thing to notice is that the channels and depth stay the same, and that's fine. But like the cool thing is that here, for example, we're arranging over every matrix which is two-dimensional. Doesn't matter what the dimensions are, right? And we encode that the output matrix has the same dimensions. So if you have a dynamically known things, it will remain dynamically known. If it's statically known, it will remain statically known, right? The other thing to notice is that we're constraining what the depth can be. So in OpenCV, the algorithms often range over a certain depth, right? In this case, this algorithm only works with words, double words, single precision floating point numbers, and double precision floating point numbers. So we can see it cannot be dynamic, because then we might fail. So we must know that it's of some depth. And this depth must be one of word 8, word 16, floated double. So this is an example where some things are left completely up to the user, for example, the number of channels, because the blurring is done per channel. So you can have whatever number of channels you want. But other things are sort of partially enforced. Like, for example, you need to have the depth, and it needs to be one of those. And you need to have a list containing 2 elements. But what's in the list doesn't matter. We just tell you that we preserve the size. Last thing, the return type has the CV except. This is just an either type where the left type variable is an OpenCV exception. So it's just to say this might fail because OpenCV might fail. Yes?
Is the type signature correct for Gaussian blur? There is a missing bracket or maybe not.
That's very likely, but is there a typo here? Yeah, there should be a bracket here. Is that what you mean?
The second line.
And the constraint.
Oh yeah.
But how should it look like?
It should look without this first bracket. Yeah, sorry, this in predicate, I'm not really explaining it because it's sort of intuitively it says it's one of those, right? But it's like type family if you're interested. Another example, edge detection, right? So Canny takes a 2-dimensional matrix with only word 8 depth, right? But this is even more restricted. You cannot pass in a float for edge detection. And, well, the shape stays the same, the depth stays the same, but the channels don't. We're basically saying the shape of this matrix is exactly the same, apart from the fact that we end up with one channel. Why do we end up with one channel? When you do edge detection, what you get out is something of the right, of the same size, of the same shape, but each value, it's something telling you if there is or there isn't an edge there. So it's going to be 0 if there isn't an edge, and 255 if there is an edge. They don't use booleans simply because I'm not sure actually, but like in general, the cool thing about this is that you can treat it as a grayscale image too. And in general, these masks are done with word 8s in OpenCV. Right. Last thing before we jump onto the demo, every matrix can also be mutable. This is very similarly done as of like if you use vector, it's basically exactly the same, but you can do things in place. I will not be really explaining it in detail because it's not worth it, but you have toe and freeze. Toe makes an immutable matrix into a mutable one. Freeze makes mutable matrix into an immutable one. And once you have a mutable matrix, you can do stuff on it. For example, this is a function that there's a circle on a mutable matrix. If you need to draw 100 circles, you don't want to copy the matrix 100 times, so you just have this thing that draws a circle in place. And without copying anything, right? It just pokes the right pixels. All right, that said, I have prepared a little demo. Actually, let's try, because otherwise you cannot see properly. So I would say that we try without, and then if it doesn't work, with a. So this live demo uses a webcam. So I've got this, this little GUI, right? And I've set it up so that there's this drop-down menu here, and I can pass in functions that modify the feed from the webcam. So let's open an editor. Now, how do I make this bigger? Why doesn't this work? Okay. Okay, is this readable for everybody? All right, so basically this run function, I have some utilities that I've prepared for this demo, but basically this run function takes a list of strings and filter. I'll show you what a filter is. And these filters are going to end up in the drop-down menu. They're basically functions that just modify the matrix, and we're going to be able to apply it in real time to the webcam feed. Now, the webcam feed is also produced with OpenCV, so there is this very convenient set of functions that lets you acquire images from the camera. It's not meant for real-time viewing. In fact, it's going to be a bit delayed. It's just, you just say, grab an image from the webcam now. What is a filter? A filter is just something that modifies an RGB image. So it's the type that I showed in that slide. It's a two-dimensional, three-channeled Word 8 matrix, right? So right now, there is nothing in that list. So it shows none on all of them. But let's write some filters. So let's write something that blurs. Blur. So we've got our import image here. For blur, we can use the function that I showed doing Gaussian blur, right? So I do Gaussian blur with to, let's say, 15 times 15. And then I can pass it in here. And I can just pass in the function that does this, and it will be offered as a choice. So let's try to build this. Oh, I didn't quit this one. So there's going to be a lot of... I have to apply it to the image, yes. Thank you, Bas. Yeah, linking is a big problem in talks. All right, so I have this feed here, and we're going to apply blur, and it blurs it. We can apply multiple times, that's fine, and it blurs it more. I hope that's evident here. There, yeah, okay. So we're blurring, 15 pixels is sort of small considering the size of that webcam. But the cool thing again is that we're just handling normal Haskell functions and strings or whatever, and it works out pretty nicely. So let's do something slightly more complicated. So let's use the edge detection function I showed. So let's call it edges. All right, so the candy function, as we said, takes an image and returns a grayscale version, right? So as a first version of the filter, I would like to just use that grayscale version as an image and show the edges, right? So I might just try to do candy image, right? Now what I know this will fail, and I want to show how it fails. Let me increase this too. All right, can you read this maybe a bit bigger? Okay, so if I try to build this, right, and I've just invoked the candy function, which is defined here, two-dimensional matrix of arbitrary channels into two-dimensional matrix of one channel, and I try to build it, I get this nice error message that says, I expected something with 3 channels because I want an RGB image, but I got of 1, right? So there is this is a type error that we will never get in C++ or Python. So let's fix that. The way we fix that is that, the way we can fix that is we use convert color, which ties in back to your question. So convert color takes the source color space, in this case grayscale, and the destination, in this case RGB, and then you pass in the the image, and it will convert the color space. Now the cool thing is that through type trickery, it basically knows what to expect for the channels for both the source and destination. So it will just know that it will end up with a 3-channeled image. I am not actually using this, so let's do that. All right. That's another very useful warning message, unused variables. Sort of a more basic technology. Okay, so I've got my feed here, and I've got edges there. And sure enough, this is actually not detecting that many edges. I probably tuned the parameters wrong. But anyway, you can certainly see that it is doing some edging. And we can blur it afterwards. Why not? We can get the edges of the blurred version, and then it gets nothing. But anyway. Or we can blur it before and get the edges later. In which case, well, yeah, this is very few edges. I should probably tune the parameters a bit. But anyway, you get the point.
Probably also the light.
The lighting is pretty good, though. Yeah. Anyway, right. So that's nice. But what if we wanted to sort of put the edges on top of the feed that we get, right? So OpenCV, when you've got this sort of masks, like the one that Edges gives you, you can copy an image on top of another only in the regions defined by the mask. So let's try to do that. Right, so what do we want to do? I want to have a red outline where I have these edges. So the way I can do this is just create a new image as big as the original one, all red, and then copy that on top of the old image. So I have this function I defined called make mat like. This is another cool thing that just takes a matrix, takes a scalar, and just makes a new matrix which is exactly like the old one, except all filled with the scalar that you give it. So let's use it. Right, image, make mat like. We want something like the original image, but red. And then we want to copy the red image onto the original image only where Edges told us so. And to do that, I need a mutable matrix to copy things on top. I don't think that's strictly true, but again, for the sake of the presentation, I'm going to create a mutable matrix. And I can do that with this other function I have defined. And these are all two-liners, right? Called modify matrix, which basically gets an immutable matrix, a function operating on the mutable version, and then returns another immutable matrix, which is the freeze version of what I've modified. And it's just, yeah, this is a very simple definition. And so I modify the image. I've got a mutable version inside. And then, what is it? Mat copy to M. I forgot myself. Right, so it's first the destination. Mat copy to M. First the destination image. Then this is the place where we want to start copying. In our case, they're perfectly overlapping. Then I think the source, or this I never remember this stuff. Right, so add image, and then the image edges as a mask. If we're lucky, this should compile. All right, we did get lucky. So let's start this again. So there is me again, and Edges now, puts the red thing on top. Now again, this is very few edges, but you get the idea. And again, I can blur later. Now, I can put the edges again, and you see, if you look closely, there are some more defined ones, right, which are the ones that survive the blurring. But anyway, again, the cool thing here, and this is what I always say when we use these sort of foreign bindings, it's that, like, when you have these really cool algorithms with Haskell, where everything is composable and nice, and you can play with it, it just becomes a lot more powerful suddenly. Okay, let's do something even more, advanced. So OpenCV has and I hope I have time for this. Probably, yeah. All right, I probably copy paste some code just to show you. OpenCV has a cascade classifier module where you can train this classifier on some data set and then use it to detect things such as faces or eyes. So OpenCV very kindly provides a sort of a pre-trained eyes classifier and face classifier. So what I'm going to do is to use that to detect my eyes and then do a sort of snapshot filter where I put like manga eyes on top of my real eyes, and it's going to overlay them right in real time, right? Now, it will be really boring for me to type it down, so I'm just going to copy it a bit and explain you what it does. This is why I was worrying about the lighting, because this cascade, it's actually not that, it's not as good as it could be. All right, let's start to build while I explain you what's happening here. All right, yes. All right, I'm going to do something like step by step. Okay, so the Haskell classifier. All right. So the Haskell classifier, you basically load a pre-trained set from this XML file. Again, they provide this already trained set for eyes. Then, well, I'll talk about the images later, but basically what it gives you is that you first convert your image to grayscale. So we're doing the reverse of what we did before because it wants grayscale images. Then you invoke the Haskell classifier and you get a list of rectangles, right? You get a list of rectangles that represent where it thinks it has matched something. So I think I should show just the rectangles first. So I'm going to loop over the eyes. And then, actually, I'm going to modify the original matrix, get a mutable version. Then I loop over the eyes. And then for each eye, I draw the rectangle on top of the original picture. So I do rectangle, which is a drawing function. Again, I forget the exact type signature. So what is it? First the matrix, then the rectangle, then the color, then the thickness. Okay, so matrix, rectangle, color, let's say blue, then the thickness, let's say 3 pixels. I'm going to comment out the rest here. All right, and we should get all the places that OpenCV thinks there are eyes in that live feed. And this is really a few lines of code. All right, now if there is enough lighting, and if I really open my eyes wide, all right, so it often thinks my chin and hair are eyes, which is a bit creepy, I guess, but you can tell, right? It's doing its job. I can even go further. You know, it's kind of working. I don't know if you can notice, but I'm really opening my eyes because otherwise if I kind of go, oh no, oh, this works better than at home. Okay, and my chin is an eye too, apparently. But let's do something nicer with this, right? So we've got the 2 eyes, and they're actually ordered by how confident OpenCV thinks there are eyes. So let's take the 2 best ones, which is what I'm doing here. The from rect you can ignore it, it's just a type thing, but anyway. So I get the first 2. If there are no 2 best eyes, I just ignore it. And then I do some like algebra, like I get the left and the right, simply the one more on the left is the last one. Then I get the center of the left one and the center of the right one. Then these 2 are vectors, so I just subtract them to get a vector from one to the other. This one. Then I get the distance, I get the magnitude of the vector, like this is just standard stuff. Then I also get like this, well, this is sort of irrelevant for now, pretend it's not there. But the first thing we can do is to see what this looks like by drawing a line between the center of the left eye and the center of the right eye, just to make sure that things sort of make sense, which is what I'm doing here. I get the center of the left eye and the center of the right eye, and I draw it in blue. So let's see how that looks like. All right, so you can see it sort of makes sense. Sometimes it goes too much in, but it's pretty impressive. So it looks pretty good. And now let's do something more fun. So I have prepared this. I've Googled like manga eye on Google Image. This has nothing to do with this Haskell filter. So I have this too. Right, I've got these 2 things, and they're green screened, as you can see. I mean, like typing down all the code to take out the green, but you basically get a mask, right? You get a mask like the edges from the green, so you get a mask that tells you what the green is. Then you load these 2, you scale them, you rotate them using that vector that tells us where the 2 centers are. You get a vector from the left to the right, you know what the pixel distance of the manga lines are, and you scale them accordingly, you rotate them, and so on. So this is what we're doing here. We got distance, we got the scale, we got the rotation, and then we scale the images. And then we copy the image. I call it masked image because, yeah, I basically paired the mask and the image at once. And we should get, yeah, you sort of have to believe me here because I cannot go and type all of it, but there are no tricks. And then I get my snapshot filter. I get, now if the face detection was better, as it is in another library that I want to bind things for called dlib, oops. Right, if the face detection was better, I would actually get control points for all the face. And if you look at dlib, that's exactly what it does. And you can basically write snapshot lenses for like, in a week. Cool thing is that I can blur afterwards, or I can, I get edges afterwards. It actually detects the edges of the eyes as an edge, right, of the fake eyes. And I can blur. Well, you can see where this is going, right? So the point here is not, the point here is that computers are really great because you can do this stuff so quickly. But the other point is that if we're able to write like these bindings so quickly for most C and C++ languages, it's really great, right? And I want to show you one last slide to sort of prove that. So this is what the bindings for the edge detection look like. That's all there is to it. I'm cheating a bit because I'm hard coding the parameters, but really it's pretty much like this. You have your function, you wrap the exception, and you handle it. Those are, again, utilities that, once you've written a couple, these are OpenCV specific stuff, and it's really easy. And then you just get pointers for your Haskell matrices, and you code C++ here, right? You code CV canny, sorts dest, you pass the parameters. In the real bindings, the parameters are also parameters of the Haskell functions, and you just need to anti-quote them as we're doing with the pointer, and you're done. So, I think this is even in my own work, we do this sort of stuff very often, especially for the initial part of a project, where you just want to see if your idea works. Because right now in Haskell, it's impossible in a lot of cases. So that's all I have. And yeah, we can have a bit more questions, I guess. Just 5 minutes, but thank you. Anyone? Yes.
The source is available on GitHub, I noticed.
Yes.
Does it run on Windows? Or is it,
That's a good question. I don't know the answer to. My guess would be no. But it's probably just because nobody's put effort into it. For example, I made it run on Mac in like half an hour. Although Windows tends to be more complicated. Yeah, the source is on GitHub. I should have mentioned this earlier, actually. It's GitHub Lumi Guide Haskell OpenCV. The documentation is actually really cool because it's got a lot of examples. Like this was successful on Reddit recently, this example here, for the Haskell classifier. But it's generally even pretty well documented, which is, props to Bas for doing this. Any other question?
I have another one.
Sure.
There is another OpenCV library for Haskell called HOpenCV.
Yes.
Do you have any words of wisdom?
No, Bas maybe does. I don't have any words of wisdom in this.
So HOpenCV targets the 2.4 version of OpenCV, and this one targets 3.1. This is the latest one. So they are,
Are they inspired by each other? Or?
No, actually, I didn't really look at HOpenCV how they did things because
So the question was, have you looked at the other OpenCV bindings? And the answer was no, because it wasn't targeting the latest one.
Yeah.
If that's fair, right? Okay. I haven't. Yeah.
So I maybe have a question.
Sure.
Because you're like a user of this library.
I am. Yeah.
I was wondering how do the type level, these phantom types in the matrix, how does that, as a user, how does
Right.
is it like
It's more of a burden. Is it more trouble than they're worth? The question is, how effective or how annoying are they? The type level features are. Personally, I totally think they're worth it. They are a bit annoying, especially in the, I think only in the sense that you have to specify more things manually. So for example, in some cases, it cannot infer the destination type of something very well. I really think they're more trouble than the opposite. I really think they're worth it. Like, they put more burden on you simply because you need to think up front about what's like the programming side with OpenCV are like NumPy, for example. NumPy in general, which is a Python library for like this magic stuff, is that you don't really care. You just hope that things are right, and sometimes things are right even if you're doing them wrong because there are automatic coercions going on. I generally don't like that style, even at the very early stages of programming. But I think that's debatable on the internet. But I think that study is going to disappear in 50 years, but who knows? Any other questions? Okay, then I think that's it. Thanks again. I'm going to